Hi everybody, welcome to my lecture series on signals and system. Today I am going to discuss about Z transformation. And first of all, myself Dr. Harish K.N., Associate Professor, Department of Electronics and Telecommunication Engineering, Sri Siddhartha Institute of Technology, Tumkur, affiliated to Sri Siddhartha Academy of Higher Education, Sahe, Tumakuru. Welcome to my lecture series on signals and system. Today I am going to discuss about Z transformation. Now, before discussing Z transformation, let us know why Z transformation is very much required. Now, we have two types of signals basically. One is continuous signal denoted by x of t. Another one is discrete signal denoted by x of n, as you already know that. Now, we have some analysis called a Fourier analysis, which, if I give any complex signal, output can be in terms of sine and cosine. Now that will be obtained only for signals which satisfies certain conditions called as Dirichlet conditions. Now if a signal is absolutely integrable for a continuous signal, then for such type of signals we can able to apply continuous time Fourier transformation, where output will be convergent in nature. And if the discrete signal which is absolutely summable, then for such signals also the output will be converging. Now there are certain signals where the output is divergent in nature. Say for example, certain constants, certain periodic signals and exponentially growing sort of signals. For all these signals, the output will be divergent in nature. For such signals, Z transformation will be applied. Now let us try to compare, what type of analysis will be applied for what type of signals. Now we have two types of signals, as I just told you: x of t, continuous signal; x of n, discrete signal. Now, and we also have periodic and non-periodic signals also. The signals can be classified into these two types: periodic and non-periodic signals. Now, what type of analysis will be applied for these kind of signals? Now, basically in the real world, we have non-periodic signals. Whatever we come across in the real time, it is always non-periodic in nature. Now, such kind of signals, what type of analysis need to be applied is what the point of discussion right now. Now, for a continuous signal, if the signal is periodic in nature, what type of analysis or what type of transform that is applicable here? That is Fourier series. Fourier series. If the signal is periodic and if the signal is continuous and if the signal is non-periodic in nature, then the signal, the transform that is applied is Fourier transform. Fourier transform. Now, for the discrete signal, if the signal is periodic in nature, then discrete time Fourier series will be applied. Similarly, if the signal is discrete in nature and it is non-periodic, then for such type of signal, we will be applying discrete time Fourier transform. Now, basically, we came to one understanding that series is applied for periodic type of signals and transform is applied for non-periodic type of signals. This is the fundamental analysis of Fourier analysis. Now, there are certain signals, as I was telling you, there are certain type of signals for which there are kind of input signals which the output is divergent in nature, as I told you, constants, growing exponential sort of a signal, etc. For such kind of signals, we go with two more type of transforms. One is Z transforms, another one is Laplace transform. Z transform is applied for only discrete type of signals and Laplace transform is applied only for continuous type of transforms, for which the output was diverging in nature in this Fourier analysis. That is Laplace transform for continuous signal and Z transform for discrete signal. This is for not only restricted to only divergent output in this case. We will apply Z transformation and Laplace transformation for all kind of signals. And moving further, we will be getting the output for such kind of signals where the output was divergent in nature in Fourier analysis. Here it will be convergent in nature up to some limited boundary. Above that boundary, here also in these two cases also the output will get divergent, but at least up to some extent we will get the output. So that is why we go with Z transformation in discrete case and Laplace transformation in the case of continuous case. Now this is just a brief introduction why Z transformation is required. Now let us move to Z transformation discussion. Now we will see the Z transformation of three important type of input. One is right-sided sequence, another one is left-sided sequence, the third one is two-sided sequence. What will be the Z transformation and the region of convergence for these three types of inputs is very important now. That will be the point of discussion. Now the first one, as I told you, x of n is equal to alpha to the power of n into u of n. Now this signal, when any signal that has been multiplied by u of n, a unit step signal, obviously the output will be right-sided because this will be defined only from 0 to infinity. Therefore, this is a right-sided sequence. Now, let us try to understand ultimately where will the region of convergence lie. Okay, now the Z transformation expression we have as x of z is equal to summation n varying from minus infinity to plus infinity x of n into z to the power of minus n. This is the Z transformation formula which we have. Now we are going to apply this Z transformation for the given input x of n is equal to alpha to the power of n u of n. Now this is equal to summation n varying from minus infinity to plus infinity. In the place of x of n, we have alpha to the power of n into u of n into the z to the power of minus n, which is equal to, now the presence of u of n can be reflected in this limit by considering the limit from 0 to infinity only, because u of n is not defined for negative time duration. Therefore, summation n varying from 0 to infinity, if I write, I can eliminate this step signal over there in that particular expression into z to the power of minus n. Now, collectively we can write this as summation n varying from 0 to infinity alpha into z to the power of minus 1 whole raised to the power of n. I can just club these two parameters because the power n is common in the power of both the parameters. Therefore, that n can be applied collectively for alpha and z to the power of minus 1. Hope this is understandable to you. Now, this is very close to finite summation, infinite summation formula, that is summation n varying from 0 to infinity alpha to the power of n. If this is a infinite summation formula, we have certain standard expression for this, 1 divided by 1 minus alpha, where alpha is not equal to 1. This is very much similar to this expression. Therefore, I can able to apply the infinite summation formula here, which is equal to, upon substituting that, I am going to get it as 1 divided by 1 minus, in the place of alpha, what do we have? We have alpha into z to the power of minus 1. Alpha into z to the power of minus 1. Now, how to obtain the region of convergence? This is an important step in Z transformation to identify the region of convergence. Once we can able to substitute or obtain this formula or this simplification equivalent to the standard formulas, either it might be infinite summation formula or it might be finite summation formula. Once we get it or reduced into that standard form, immediately we need to take the region of convergence. The condition is whatever the alpha we have, that alpha should be less than 1. In the place of alpha, we have alpha into z to the power of minus 1. So that parameter, alpha z to the power of minus 1 modulus, should be less than 1 always, which is very much similar to that of that condition. Okay, in order to have this infinite summation formula applied to this parameter, we need to consider this particular condition, and that is the region of convergence condition. Now we need to simplify this. How to simplify it? Alpha Z inverse can be written as alpha divided by Z, because Z inverse is 1 by Z, which is less than 1, and finally that can be obtained as modulus of alpha less than modulus of Z, or modulus of Z is greater than modulus of alpha. This condition we call it as region of convergence. And upon simplifying this expression, in order to obtain a simplified version of the output, now I can able to simplify this. What can I write in the place of this? Because this is Z inverse. Z inverse can be written as alpha divided by Z. And once that Z is cross multiply, what is that I am going to get? 1 divided by Z minus alpha. Now this is what I can able to obtain upon simplifying it. Therefore, and divided by alpha, when Z is also there, because upon cross multiplying, denominator Z will also be there. Upon moving this to the numerator, we are going to get it as Z divided by Z minus alpha, with the region of convergence modulus of Z greater than alpha. Now this is what the region of convergence, and this is the Z transformation of the given input alpha to the power of n u of n. Now hope you remember this. We will move on to the next sheet. Therefore we have obtained x of Z, the Z transformation of the given input x of Z, as x of Z is equal to Z divided by Z minus alpha, where the region of convergence modulus of Z is greater than modulus of alpha. How to draw the region of convergence then? In Z transformation, the plane which we will be consider is the Z plane, which is a complex plane. Now this is real part of Z will be on x-axis, and imaginary part of Z will be on y-axis. Now, as per the condition of region of convergence, modulus of Z is greater than alpha. Now, we need to consider the circle of radius alpha in order to draw the region of convergence. Now, that plays a major role in order to decide the stability of any system for that matter. If the stability is known, we can able to analyze how the system behaves. Now, how to identify the stability? This, region of convergence, if it is outside, it can be outside the circle of this radius, or inside the circle of this radius, or it can be inside the concentric circle. Now it depends on the location of poles and zero. The stability can be analyzed with the help of the location of poles and zeros. How to identify poles and how to identify zeros in this particular expression? Now, for whatever the value of Z, this expression x of Z becomes infinite. Those values are the location of poles. For whatever the values of Z, the expression x of Z becomes 0, then that values or those values will be the location of zeros in this ROC plane or in the Z plane. Now, for what values of Z here, this expression x of Z becomes infinite. How do we get infinity? Anything by 0 obviously will make this particular expression equal to infinity. Now anything by 0, how to make this 0? Upon equating Z is equal to alpha, alpha minus alpha, it becomes 0. Therefore anything by 0 is equal to infinity. Now x of Z is becoming equal to infinite for whatever the excuse me. Now as I told you, for whatever the value of Z, this x of Z becomes infinite. Those are the values of poles. Now, what are the values of poles? Z is equal to alpha. Now, this is the circle of radius alpha. Whatever the location you consider on this circle alpha, that is where the pole is located. And to be more specific, this has been considered as plus alpha. Therefore, we consider plus alpha as the location of pole. Now, the pole is located on this circle. If alpha is equal to 1, then this system which has obtained this particular output will be marginally stable. If the pole is located inside the circle of radius 1, then the system is said to be stable. If the pole is located outside the circle of radius 1, then the system is said to be unstable. This is how we can able to analyze the stability criteria of any discrete system with the help of Z plane or with the help of region of convergence and location of poles and zeros. Now obviously when I located the pole, I also have to locate the zero. Where are zeros located? Now for whatever the values of this Z, this x of Z becomes 0, those are the values of location of zeros. Now which is the location of 0 for what value of Z this x of Z becomes 0? Now straight away if I substitute Z is equal to 0, then this x of Z will become 0. That is where the pole when 0 is located. Now Z is equal to 0 is the location of 0. Now pole is indicated by a star. 0 is indicated by a small circle. This is how the pole and 0 are indicated with respect to Z transformation. Even if you see in control system, this is how pole and zeros are indicated. Now we have marked the location of pole and 0, and this is the circle of radius alpha as per the region of convergence, and where the region of convergence lies, it is greater than alpha. Therefore the region of convergence lies after this circle of radius alpha. This is what the region of convergence we can identify in our case of the input. The region of convergence is modulus of Z greater than modulus of alpha. Alpha can be either plus value or a positive value or a negative value. Therefore, it is a circle. Normally, we represent the region of convergence in the form of a circle. Even without circle also, we can able to identify the region of convergence down the line. When we discuss that numerical, we'll come to know. Now, this is the region of convergence. Now, what does this literally mean? If I consider any values within this circle, then the output will be divergent in nature. If I consider any value apart from this circle of radius alpha, above that circle of radius of alpha, wherever we have marked and hashed lines, if I consider any value in that region, then the output will be convergent in nature. We will be getting a finite value. We will not be getting any infinite value. That is what, converging output. That is why that region is called as region of convergence. This is with respect to the input x of n is equal to alpha to the power of n u of n. Now let us see the other second input, left-sided sequence. This is for a right-sided sequence. Now one more point to be remembered here is the region of convergence for a right-sided sequence is outside the circle of radius alpha, right? Now for the second input, if I consider x of n is equal to minus of alpha to the power of n u of minus n minus 1. Now obviously you can easily identify this particular sequence is a left-sided sequence because u of minus n minus 1 is located towards the left-hand side of that xy plane, isn't it? Therefore, whatever if I multiply for this u of minus n minus 1, that output, that signal will be obviously left-sided. Therefore, this entire signal is a left-sided sequence. Now, let us see the output or the region of convergence where it lies, either towards right side the circle of radius of alpha or inside the circle of radius of alpha or within a concentric ring. Let us see. Now, this is the input we have. The Z transformation expression, we already know that x of z is equal to summation n varying from minus infinity to plus infinity x of n into z to the power of minus n. This is what the Z transformation expression. Now if I substitute in the place of input, what do I get? Summation n varies from minus infinity to plus infinity minus of alpha to the power of n u of minus n minus 1 into z to the power of minus n. This is what upon substituting the given input in the expression, which is equal to, now minus I can take out of summation, I can just place it before summation itself, minus summation Now, u of minus n minus 1, from where to where this particular signal is defined. Let us understand that first before solving the output or getting the output, Z transformation output for this given input. U of minus n minus 1. Let us begin the analysis from u of n. U of n is defined from 0 to infinity. It is been shifted towards right side by 1 unit because of the presence of minus 1. Then from where to where now the signal will be defined. If I consider u of n minus 1, then it will be defined from 1 to infinity, still positive. Now minus n is there, it's a time reversal operation. The entire signal which is defined from 1 to infinity will be time reversed. Now from where to where the time reversed signal will be defined now. Now considering u of minus n minus 1, from where to where this signal, to be specific, is defined from minus infinity to minus 1 only, isn't it? It is not defined, no values is there from 0, 1, 2 or till infinite. It is having a value of 1 unit from minus infinity to minus 1. Therefore, it is a purely left-hand side signal or a left-sided signal, isn't it? Therefore, this is a left-sided signal being multiplied with alpha. The entire product or the entire signal is also a left-sided sequence. Therefore, this signal from where to where it is defined, as we analyzed just now, it is defined from minus infinity to minus 1. And alpha to the power of n is there, and the value of u of minus n minus 1 will be always 1 because its coefficient is 1. Therefore, into 1, if I consider that or not, it doesn't make any difference. And z to the power of minus n is there as it is, we have represented. Now, this is equal to minus of summation n varying from minus infinity to minus 1 alpha into z to the power of minus 1 whole raised to the power of n. Can I write it like this collectively? Because the powers are same, the bases can be added here. Therefore, this summation minus infinity to minus 1 with a collective power raised to n is been considered here. Now, you need to understand this is a summation. 1, 2, 3, 4. I mean, if I add 1 plus 2 plus 3 plus 4, what will be the result? Now, whatever it is, now the exact answer will be obtained if I add 4 plus 3 plus 2 plus 1, isn't it? Does it change? Never. Whatever I add, either from this side or that side, summation will remains the same. In the similar way, if I add from minus infinity to minus 1 or from minus 1 to minus infinity, the output remains same. Therefore, I will be considering the limit instead of from minus infinity to minus 1, I will be considering it from n varying from minus 1 to minus infinity. And the parameter inside the summation remains the same as it is, which we have not at all altered yet, which is equal to, now I need to make this into a standard summation formula. What do we have? Because of the presence of infinity, it has to be an infinite summation formula. Now, I need to make this equal to or similar to infinite summation formula because of the presence of infinity over here. How to make this into a standard infinite summation formula? I need to have 0 in the lower limit. I need to have plus infinity in the upper limit. Now, how to make it 0 and plus infinity? If I eliminate this negative sign in the limit, what change I need to make it here in the power of this particular parameter? I can just write it like this, try to understand, n varying from 1 to infinity. I am just changing the sign of the limit. Therefore, alpha z to the power of minus 1 to the power of minus n if I write, then that is equal to this particular expression. If I change the negative, I mean the sign of this limit, the sign of the power need to be altered. If I need to change it back to minus, that is minus 1 to minus infinity, once again I need to change the sign of the power to positive. This is how both the ways it can be reflected, by maintaining or by without changing the meaning of this particular expression. Now, this is still not equal to standard infinite summation formula, isn't it? Which is equal to, now how can I make the lower limit equal to 0? by subtracting by 1, isn't it? Now, how to change it? N is equal to 1 minus 1, infinity minus 1. If I am doing this operation with respect to the limit, then what change I need to see? Now, in the power, since it is minus, I am reflecting that minus inside it. Therefore, I am making it as alpha to the power of minus 1, z to the power of minus into minus, it becomes plus. Therefore, once again, this is becoming n, positive n. Now, since I am subtracting some value in this limit, I need to add the same amount to the power. Therefore, n plus 1 if I make, then I am not at all changing the meaning of this particular expression from here to there. Isn't it? Now, it is, I am subtracting 1 with this limit. In the same way, I am adding the same amount 1 to the power. Thereby, that meaning of that particular expression is unaltered. This you should remember it, and you need to do this very carefully. Now, what will be the result of this manipulation, which is equal to, therefore just try to remember this. We will be moving to the next page. The expression which we got was minus of summation n is equal to 1 minus 1, infinity minus 1, alpha to the power of minus 1, z whole to the power of plus n plus 1. Since we had subtracted, we are adding it as we are continuing from the previous step, which is equal to, now what will be the limit? N becomes equal to 0. Infinity minus 1, it becomes infinity itself. Now, alpha to the power of minus 1, z to the power of plus 1, whole raised to the power of n into alpha to the power of minus 1 into z to the power of plus 1, isn't it? This power has been splitted now. Okay. The base has been applied with two different powers according to this here. The base raised to the power of first power, and the same base raised to the power of second parameter 1 here. Now, since there is no variable of summation in this particular parameter, we can take out that parameter outside the summation. That becomes alpha to the power of 1 into z into summation n varying from 0 to infinity, alpha to the power of minus 1 into z whole raised to the power of n. Now, my dear students, can I correlate this particular expression equal to or similar to standard infinite summation formula, which we have summation n varying from 0 to infinity, alpha raised to the power of n is equal to 1 divided by 1 minus alpha, where alpha is not equal to 1. That standard infinite summation formula, if you can able to remember, that is very much similar to that of this. Now, I can correlate that and I can substitute that equation here, which is now equal to, minus is also there, which we should not forget it, minus alpha raised to the power of minus 1 into z into that standard infinite summation formula. Upon applying it here, it becomes 1 divided by 1 minus of, in the place of alpha, what do we have? Alpha raised to the power of minus 1 into z, where I told you before, immediately after obtaining this or simplifying the expression into the standard summation formula, we need to apply the region of convergence condition. What is that condition? Whatever that is there in the place of alpha, that modulus should be always less than 1. Now, we need to simplify this. Let us simplify it further after obtaining the expression for this. Now, this expression becomes, which is equal to minus of alpha to the power of minus 1 into z divided by, now in the place of this alpha, inverse is there. That inverse is nothing but z divided by alpha. That alpha, if I cross multiply, what happens? It becomes alpha divided by alpha minus z. Hope you have understood this. Now, this will be equal to minus of z divided by alpha. This inverse has been moved to the to the denominator, alpha into alpha divided by alpha minus z. Yes, x of z, as you can see above, is equal to alpha inverse into z divided by 1 minus alpha inverse into z, as per the infinite summation formula. You can watch it previously. As per that formula, we have arrived at this particular expression, and if we could able to simplify it, we will be getting minus z divided by alpha. As alpha is having an inverse power, it will come to the denominator and will be multiplied by 1 divided by 1 minus z divided by alpha, a similar case, which is equal to minus z divided by alpha into alpha minus z divided by alpha. Dear students, you can able to observe two alphas in the denominator, alpha and that alpha denominator's denominator will get cancelled out, right? And hence it is equal to minus z divided by alpha minus z will be the remainder ultimately, and in the denominator we want to get the expression as z minus alpha. So what can we do for that? Minus can be taken out as a common factor, and in the numerator we have minus already, and in the denominator, if we could able to take out minus as a common factor, we will be going to get the expression as z minus alpha with a minus as a common factor. Therefore, minus in the numerator and minus in the denominator will become plus, good, and it is equal to z divided by z minus alpha. This will be the z transformation of the given expression. And it is very important to know the region of convergence. That is what the Z transform is well known for. We need to plot the region of convergence. And as I told you before, immediately after applying the formula, that is infinite or finite summation formula, whatever in the place of alpha we have, that we need to consider for the condition of region of convergence. What is that expression? It is in the place of alpha, in the standard form of infinite summation formula we have, that is alpha inverse into z modulus is less than 1. This is what the condition we have to get it in order to apply that infinite summation formula that we have considered here. And since alpha is having an inverse power, it becomes z divided by alpha modulus less than 1. Now upon cross multiplying alpha to the right hand side of that greater 7 or lesser symbol, what does it become? It becomes modulus of z less than modulus of alpha. Now where does the region of convergence lie? It will be in the circle of radius alpha and within that circle of radius alpha, isn't it? Therefore, modulus of z less than modulus of alpha is the region of convergence for the given question, and the z transformation is x of z is equal to z divided by z minus alpha. Yeah. Now, we have located or marked the location of pole, and we have also marked the location of 0 in this particular z plane. Now, the region of convergence. Where does the region of convergence lie? It is less than alpha. Therefore, less than alpha means it should come inside the circle of radius alpha. Now, this is where the region of convergence lie. My dear students, you have to observe carefully. Here, in the previous case, for a right-sided sequence, the region of convergence was located outside the circle of radius alpha. Now, my dear students, the region of convergence have been identified to be located inside the circle of radius alpha. This is where the region, this is what the region of convergence is. Now, for a left-sided sequence, region of convergence lie inside the circle of radius alpha. Here it is alpha, therefore inside the circle of radius alpha. And for a right-sided sequence, the region of convergence lies outside the circle of radius alpha. Now, for now, we will stop our discussion, and in the next class, let us try to understand what will be or where will the region of convergence lie for a two-sided sequence. Okay, and finally we will list out the properties of region of convergence based on the analysis or the output that we have got so far. Thank you very much for now. See you.